All right, so let's get started. So this stick looks bent, right? Why does it look bent? Why does it look bent? All right, so some of you guys know the answer. So if you know the answer, just jump in at this point.
Because water diffracts the light, so when it bounces back and hits our eyes, the stick looks bent.
Okay, so Lucas, you said that the water diffracts the light, or did you mean to say refracts the light?
Come again?
Did you say the water diffracts the light or refracts the light?
Diffracts.
All right, Lucas, I'm going to give you 5 points. You meant to say refracts, right? This is refraction.
I got you.
Okay, well, what's the difference between refraction and diffraction? So you'll know, we'll cover that stuff at some point. All right, so something happens to light. So in your mind, what does it mean? This it looks bent. Forget the terminology. Tell me what's going on here that makes it look bent.
The light is bouncing off the water at a different angle, and when that light hits our eyes, it registers it as the stick is bent.
Okay, so do you know why that happens?
The properties of water? No, I really don't know.
Okay, sure. Fine. That's not bad. All right, so that's a good start. I'm gonna give you 5 points for that one. Additionally, all right. So diamonds sparkle because why do diamonds sparkle? All right, going once, going twice. No one is saying anything. All right, so which means that we gotta talk about something that you can answer for a change. All right, so what's a sparkle? All right, so that didn't go anywhere either. So what causes sparkle?
Light hitting the diamonds at different angles.
Okay, so what happens to light hitting the diamond or diamonds at different angles?
It bounces back off of your eyes.
All right, so it's not a bad idea. I'm gonna give you 5 points for it. So somehow the light is getting bounced off from diamonds, right? So what's a sparkle? Sparkle is exactly what it is. Sparkle is this, guys. This is what you see. Sparkle is generated when light escapes from diamond, and the light is gonna escape from diamond only at certain angles. Every time you see light escaping, it's gonna register as a sparkle. All right, so why is it that diamonds are sparkly? This is probably the most important question that I'm going to ask today, and this normally would take us into modern physics. Obviously, this course is not in modern physics. Modern physics is an extension of this one. So you got the white light going through a prism, breaking into its color components. All right, so I got 2 questions for you. Question number 1: why does the white light break into its color components? What caused that to happen? Next question is, the most important one is, why is that red is on top and the blue is at the bottom? All right, you don't quite see it clearly here. The violet should be at the bottom, but I kind of like the separation between red and blue here. It's very clearly illustrated. So why is it that red is on top, blue is at the bottom?
Because of the wavelength.
All right, because of the wavelength. So what does that even mean? I mean, how does the wavelength factor into this? All right, speaking of wavelengths, which one is a larger wavelength, red or blue?
Red.
Okay, and why does it matter that the red is a larger wavelength? And furthermore, what causes color separation? All right, so those are the questions we will get to investigate. All right, so we talked about electromagnetic waves last time, at least conceptually. The only thing I want you to know is the comparison between the wavelengths, between red and you got the violet. So we got the red as well as we got the violet. Okay, I don't even care about the red or violet. I usually like to focus on red and blue, the way we experience it. All right, so the thing to notice between red and violet, let me check to see which one I like better. All right, so the color red, you got that. Ignore the fact that this is 10 to the minus 7, so that's fairly small. This is roughly about 8, and blue is roughly about 5. All right, so if that's the case, which one has a larger wavelength? Is it the red, or is it the blue? All right, that's the only thing I want you to remember. All right, so red is gonna have a wavelength which is gonna be larger than blue. That's it. That's all the background stuff that you need right now. Red is gonna have a larger wavelength than the blue. All right, so we discussed how light is created last time, a number of times actually. We said that the electron inside atoms undergoing quantum jumps is how light is generated. So the electron jumping around inside the atom is gonna emit light. When the electron jumps from a higher energy state to a lower energy state, according to modern physics, the light is being emitted. So the excited electrons inside atoms actually glow. That's what it means. They will just generate light. Okay, I want you to focus on the color of light in this case, or not the color of light, color of the electron. It looks yellow. All right, so let's go from the modern theory to the classical theory. Focus on the pulsating sphere. What's the color of the pulsating sphere? Once again, it's yellow. It's just coincidental, like end up getting used from 2 different books. So the electron jumping inside an atom becomes the pulsating sphere in classical physics. So the pulsating sphere is going to glow, which means that's going to emit light. Light is going to be emitted spherically. All right, so you're looking at the way the light is being emitted spherically. So it's going to travel from the source, away from the source at the light speed. These are known as the wavefronts. And if you draw lines perpendicular to the wavefronts, so these are your wavefronts. And if you draw lines perpendicular to the wavefronts, you end up getting, okay, cube. So these are lines perpendicular to the wavefronts. So these become your light rays. All right, so we will do the ray optics next week. This stuff is actually fairly easy. Let's focus on the conceptual physics behind it. All right, so you got the incident ray coming in this direction. This is the reflected ray. And here's your angle of incidence. This is the angle of reflection. Angle of incidence and the reflection is measured with respect to the normal. And according to the line of reflection, angle of incidence is going to be the same as the angle of reflection. That's it. All right, so this is your high school physics right there. That covers it. Okay, so my question to you is, what happens right at the surface over here that causes reflection? All right, so the light comes in and then interacts with the atoms and molecules making up the structure, and then somehow you end up getting a reflection. So mirror surface in this case, it's a mirror is made up of metal, usually. The reflection is caused by the metal. So the metal is going to have conduction electrons, and somehow when the light interacts with these conduction electrons, you end up getting a reflection. So the question is, what causes that reflection?
An even more important question. Since everything ever seen is the result of light encountering matter, the question is, what is the nature of that encounter? And the answer is, since all matter is electrical in nature, it all comes down to light waves and electric charges. For example, when a light wave encounters an electric charge, the oscillating electric field makes the charge oscillate, which creates a new outgoing wave. Notice the shadow that forms behind the oscillating charge. A line of electric charges, it might be electrons bound to atoms in a crystal, can produce outgoing plane wave fronts in new directions. And if the charges are free to move easily, as are electrons inside a metal, the result can be to stop the wave from penetrating at all. Instead, the wave is completely reflected. This is mirror reflection, in which the angle of incidence is equal to the angle of reflection. That's true no matter from what direction the beam arrives. But reflection can also be described in a different way. Of all the possible paths from source to mirror to destination, the true path is the one that arrives in the shortest time.
All right, so what causes reflection on the atomic level, or at the atomic level? All right, so what you guys get out of it?
Pulsing electrons?
Okay, that's not bad. Explain more if you can. All right, so the pulsing electrons.
And even more important, from what direction to which the instead move easily. And if the charges are free to move easily.
Okay, number one, you're dealing with free charges.
As are electrons inside a metal.
Those are the conduction electrons.
The result can be to stop the wave from penetrating at all.
All right, so they will pulse.
Instead, the wave is completely reflected.
And then the wave is going to get reflected. Okay, guys, the way I explained it is kind of the way you guys explain questions on the test. Out of 2 points, my explanation is worth less than 1 point. While it's not inaccurate, it's incomplete.
This is mirror reflection, in which the angle of
this video almost does a good job.
crystal
Okay, a couple of
makes
things.
the charge
You got a single charge.
oscillate,
So what happens, the charge under the influence of the electric field
which creates a
is going to oscillate back and forth.
new outgoing wave.
And the accelerating charges do generate electromagnetic waves, so it's going to end up generating its own electromagnetic waves. So it's going to act like an antenna in a sense. And so the waves will interfere destructively or destructively as well as constructively.
Notice the shadow that forms behind the oscillating charge.
All right, so that's the shadow.
A line of electric charges, they might be electrons bound to atoms in a crystal, can produce outgoing plane wave
All right, so the oscillating charges will create their own electromagnetic waves.
fronts in new directions.
You end up getting these cancellations here, so there's not going to be much of a penetration behind it. And the newly generated electromagnetic wave will cause interference patterns with the incoming ones. And it so happens that the only surviving ones will be the ones being reflected at the same angle as the incoming one.
And if the charges are free to move easily, as are electrons inside a metal, the result can be to stop the wave from penetrating at all. Instead, the wave is completely reflected. This is mirror reflection, in which the angle of incidence is equal to the angle of reflection.
Okay, cute. Let's stop this. All right, let's solidify that. All right, I recorded the lecture already for the RLC circuits. All right, so I'm gonna edit it and put it online for you guys to watch. Okay, so you'll be responsible for this stuff for Sunday's test. All right, so we started a new topic. All right, so we are working on optics right now. Just the background stuff. You know, we'll get the mathematics on top of it, overlay the math. All right, so what do we know? We have been talking about reflection. All right, so this is the non-reflective surface. This portion is non-reflective, and this portion is going to be reflected. Incoming, incident ray, reflected ray. I is incident, R is going to be reflected. And the angles will be measured with respect to the normal. So that's what we got. All right, so you got the normal. You got the incident ray. And we got the reflected ray. Angle of incidence and the angle of reflection. They will be equal to each other. All right, so this is known as the law of reflection. All right, the physics that we're interested in is what goes on right here. There are two types of electrons in physics. You got the free electrons, like the conduction electrons that you find inside metals. And then you have the bound electrons. Those are the ones that are part of an atom. Okay, they don't quite interact the same way with light. Free electrons, when the light comes in, is an electromagnetic wave, so it's coming in. I'm focusing on the electric field component. All right, so as if it's just coming in this direction. All right, so this is E that you're looking at. I'm only focusing on the electric field component. What will the electric field component do? Just interacting with light is going to shake it up and down in this direction. So it's going to make it accelerate up and down. So in turn, this accelerating motion is going to generate its own electromagnetic wave. And you know that the waves interfere constructively and destructively. It just so happens the only surviving component is going to be in this direction. So its electromagnetic wave gets re-emitted in that sense. All right, so this is your incident, this is your reflector. All right, so that's what we get. All right, so this is our reflection phenomena. Atomic electrons will behave differently. What the atomic electrons usually do, they will literally absorb the incoming light. So they will absorb the incoming light. All right, so this is the incident light. And then they will become energized. Upon being energized, they will jump up to a next orbital or energy state. And they will stay there for a fraction of a second. Upon jumping down to the original state, they will release that energy. All right. So that energy is going to get re-emitted. So this electron is going to undergo a quantum jump. It's going to jump up here, stay there for a fraction of a second. And upon making a jump, all right, so I'm just going to, I don't want to put the electron at the same spot. It's just a random occurrence anyway. So upon jumping down, it's going to release that energy in the form of light. It gets released. Notice that the direction is kind of random. This is incoming, and this is the light which is released at a given direction. I'm going to put S here. The reason why I'm putting S there, because this is called scattering.